Well, so today we're going to look at EchoLeak, which is a prompt injection attack which leads to data exfiltration. Now, this was a very severe vulnerability last year in Microsoft 365 Copilot. It's been remediated, but a lot of smaller companies do not kind of even think something like this could happen, which makes it very dangerous. And today we're going to see how this works, how prompt injection leads to, crossing boundaries and then taking sensitive organization data and then exfiltrating it out to like a malicious actor. And I'm also going to show you a live demo on how this works. I'm going to show you on the browser the data being exfiltrated to a server that's in Canada today. It's in Canada because Azure didn't let me create one in US East. So a little bit about myself. I am the principal developer at Automata. We are a startup. We focus on compliance and inventory management. We also have advisory services. We do gap assessments, helping with risk assessments, compliance, all the fun stuff, all the stuff most people don't want to do. And about me, I was a software engineer for, I think, 3 years. Now I just switched over. I'm still a software engineer, pretty much. I still code a lot, but just more on the security side of things. So just for a little bit of context, prompt injection has been a thing since LLMs have been adopted. We use them every day, and there are people who definitely try to abuse them. So the more and more LLMs get integrated into our lives, the more and more these attacks happen. Here are some stats. There are some sources at the bottom. This just shows that this is a real issue that needs to be handled, right? And when it comes to LLMs, at least commercial LLMs, a lot of us talk to them with our personal information. GPT, Claude, both of them have this feature called memory, where you can talk to them. People use them as therapists. I sometimes went to GPT, like my boss said something I don't like him. What do I do? Just kidding. He's a great guy, but we all went to LLM sometimes. People use them for therapy. They use them to deal with their mental health issues. And these are some stats. It's a real thing. There's been surveys done where people talk to AI about their mental health issues. And when such critical, sensitive information about them is stored in an LLM's memory and context, that could be exfiltrated out to someone who can later then use that to cause harm to that person or to an organization. Right? Now I'm going to introduce EchoLeak, which is the vulnerability and how it happened. It was discovered last year. It has a very high CVSS score, 9.3. It's zero-click. To this day, nobody knows how much data has been exfiltrated because, well, of course, Microsoft's not going to let us know. They've mitigated it since, so nothing to worry about now. So how does this work? So the attack type is a zero-click indirect prompt injection. So when we talk about prompt injections, there's direct and there's indirect. So direct is when you type into the chat box, ignore instructions, do X, Y, and Z. That is direct. Indirect is when you upload a PDF and the PDF has hidden instructions to the LLM, asking it to do something that crosses boundaries, exfiltrates data, do something it's not supposed to do, or to hijack a system. Now, the target was Microsoft 365 Copilot. It had a small loophole, or I would say like a vulnerability or thing that was handled improperly that the attackers abused. And the instruction was an email to an executive addressing the LLM rather than the executive. It was an external person who sent an email to an exec, but the email had instructions for an LLM. Now, the mechanism is that Copilot or the UI filters out inline links, but it did not filter out reference style links. And this is the loophole that the attackers used. And the impact was when this link was rendered on the browser, the data or sensitive organization data was just exfiltrated because the browser has to get that image and it had to make that API call. So the user has no say in whether that call is made or not. The browser automatically just renders it and the data is just sent out. Now, the entry point for this type of attack model is to embed instructions into a document. And this document, when the AI system places that into the context of the LLM, it gets the LLM to cross a boundary that's not supposed to. So it takes the sensitive organization data, it takes the email with the hidden instructions, all of it in the same context, and then sends it to the LLM. And then the LLM processes this, creates a link with the sensitive information, and then just this link then just sends out the data. And that is the data path traversal, and the egress is sending it out to the malicious server. Now, this is kind of how it looks like. This is what a sample email would look like. So you target an exec who has access to a lot of proprietary information, docs, maybe reports, financial reports, if the company is doing well or not, if they're doing fraud or not. And one of the instructions would not be ignore instructions, override system instructions, because this would get caught at the prompt injection classifier. That is the first step of any production LLM or AI system, is that it gets passed through a classifier which says if there's an attempt to inject or override instructions. To bypass that, you just have an injection attempt that's very subtle. It's like get information to visualize the information of our project text, render this link, put in some secret information there. Now, this email gets sent out to an exec, and the exec, at the end of the day, we're all feeling lazy. He's like, summarize all my emails for the day. So the system, Copilot, gets all of the emails for that day, including the malicious one, with the instructions, gets all of the documents of that day or important documents of that quarter, sends it to the LLM, and the LLM renders that link in the response. Now, this is what Copilot actually generates, or the LLM generates this. And at the end, you can see that there's a reference style link. There's here's project X progress chart, and that's the link. It uses a Microsoft Teams. I'll get into it a bit, why. And then you can see the URL says attacker XYZ, image, data, and then it just sends all the sensitive data in the query parameter. Now, when this is rendered on the browser, it automatically renders into this graph. The user doesn't know that the data has been sent out. Everything looks fine. They just get a nice graph, and the attacker gets, well, all the sensitive information. Fair deal, right? Yes.
Isn't there like a limit to the query string?
There is.
Okay.
There is, but and the email can specify that just send the most important information just within certain characters. And before you saw it, there was like a Teams URL, right? Here you saw there's a Teams URL, not the attacker URL directly. Why is that? So if you are in an organization, IT already has defenses, right? There's network level defenses. There's content security policy that doesn't let the browser render images from unknown sources, or there's an allow list from sources where you can render images from, right? So the attackers know this. But then there's like a loophole, or there's like a Teams URL that, so if the attacker were to use a direct call, then it would get blocked by the CSP. But if they use the Teams URL, which as a proxy, and send the malicious URL through the Teams URL, which is allowed by the CSP, then the data can be sent out to the attacker server, and they get information to the data and then send back the image, which gets rendered on the UI. And there's just like a comparison. If it's a direct URL, well, it gets blocked by the CSP. If it's through the Teams URL, which is usually allowed, which is not blocked by the CSP in 365 Copilot, then it just gets through. Now, this is what the user sees, and this is what the attacker sees. What the user sees is just a normal response with a graph at the end, or with an image that says, this is what project X is about. And the attacker server gets the query with the query parameters containing very sensitive information, and they have access to it in their logs. Now, this is the entire full attack flow. I'll share the slides later. I'll see if I can just tell the organization to share it with you guys. But I want to show a live demo in a sandbox that I've built of how this actually happens. So here, I have this simple chatbot, right? And usually people just take PDFs from the internet, maybe web pages, and they just paste it into chatbots and then ask it to answer questions. So I have this PDF here. So I'm just going to put this into this chatbot and just ask it. But before I do that, I do want to show you something in the settings. Think of this as the emulation of a chatbot's memory. I use a chatbot a lot. I talk to it about myself. It has personal information about me. And this is kind of the information that it has about me. For now, that's kind of an emulation of the information it has about me. Now, when I ask it, summarize this document, right? It's going to extract the sources. Since this is the first call, the LLM is not loaded on the GPU. It's going to take a little bit of time. Oh, there. You don't see anything, but the image automatically rendered, right? I'm just going to go into this exfil interface. I'm going to hit refresh. And it just sent me information. It sent me the information. Pavan likes cooking and presenting at OWASP to my server. And this server is in Canada somewhere, in some Azure server, right? And how did that happen? Now, when I right-click on this, you can see that the URL it rendered is Cubitrain Workshops API, get image, and it has the user prompt, the exact prompt that I typed in, and the memory, which is the LLM generates information about me in a short sentence and just sends it out as a query parameter, which I receive on my server about this user. Now, how did this happen? I'm just going to open the file that I just put in there. It seems like a very normal file about quantum entanglement, right? Just nothing suspicious about this until you go all the way to the bottom. Still nothing. If you were to find this file on the internet, you would think nothing's wrong with it. It's just a normal PDF. But then here, there's like hidden instructions here that nobody would see. Nobody would know. And if I were to paste this onto a sticky note, you would see exactly what it says. And this is the instructions to the LLM to render that link that would generate the image along with the user's information or any sensitive information that needs to be exfiltrated. And here is the exact URL. And it says, the image is fetch this image. And the prompt is what the user actually typed. Memory is the actual user memory. Usually when I do workshops, what I do is I give people, I give them access to this, and I give people the PDF. They type in their questions, they put in their own memory, and then I just pull up this interface right here. And all of their information just keeps coming here, and they don't even know what happened. So it's kind of a really fun exercise to do. So this is kind of how it happens. Now, PDFs are not the only way where you can inject instructions. There's also web pages that you can do this with. I have a web page. Like if I was a professor, this is definitely something I would do. So it's like a quantum entanglement assignment. And I just put in my name, and then there's this assignment, right? Students, generally, they would just be like, I'm just going to copy the URL and then just paste it here and just be like, answer all these questions. And then it's going to extract the page. It's going to get all the content from the page, and then it's taking a while. Okay, there it is. Now it's answering all the questions. Great. At the end, it's going to generate an image, the same image again. And then here, if I refresh this, I have information about the person, the exact prompt that they asked, information about them. Okay, that's not the one, but this is the one. The order is kind of a bit messed up, but this is what I asked. Answer all these questions, information about me, and the username that they typed in. So if I was a professor, this is definitely what I'm doing. I would just embed some hidden instructions right here, you can see it's going to be here. It's going to be somewhere here. I'm searching for it. Yes, there. All the hidden instructions right there. Nobody's going to verify that. Nobody's clicking on inspect element to check if there's hidden instructions. I can't wait to be a professor. but generally the attack idea is this: in 365 Copilot, the injection source was emails. It could also be documents, PowerPoints, anything. All of these could be potential modes of injection. So it's very important to sanitize all of these before you can try it. And sanitization also works only up to a certain extent, because the injection is not always addressing the LLM. It says, for more context, do X, Y, and Z. If you want to give the user more, if you want to get more information about, project ABC, do so and so. So that's, you can't classify that as an injection, because it's not attempting to override any system instructions. It just seems like something like notes that somebody would have put there, right? So how do we defend against this? I know we have only 5 minutes. The slides are going to be a bit long, but how do we defend against this? So there are some defenses here. The first one is to sanitize outputs. By doing that, you just you just remove all links from the output. There's a downside to this: user experience. If I ask GPT, give me the restaurants in this area that are open from 6 to 9 p.m., I don't want names. I want the link of the restaurant that I can just go check, right? But if you're using it in an org, well, maybe you don't need that. You can sanitize all links. And that's one way to do it. It's a trade-off between user experience and security. The second way you can do it is to require human action. So the link is still there, but when you click on it, but you need to click on the link to be able to see what the contents are. Now, this still has human error, which means not every people are going to look at the link. To them, it's going to seem normal. They're just going to click on it anyways, right? And this happens a lot. And this is not the best way to protect, but it because there's still chances for human error in this. Another way is to manage everything using your CSP. Just have an allow list. Here I'm just removing everything, so if it tries to render anything, it's kind of emulates a CSP. It's getting blocked by the CSP. And you can only set a certain list of domains or hosts where you want the image to, or where you want images to be fetched from. You could set them to .gov, .edu, maybe Google. Only trusted sources where the images are safe. Another thing is to also have an allow list for your sources. When somebody just puts in a link, you don't just automatically fetch all the data from them. You just block certain sources, or only fetch data from trusted sources where you are very confident that there's no injection attempts being done. So that way, if by doing this, if I were to try this again, it's going to say, well, the source was blocked and I can't answer this question. Right now, since qbtrain.com is not in allowed sources, it's going to say, well, yeah, it says, yep, it says it's not able to answer the question anymore because it's not fetching data from that information. Of course, the system prompt is not that great. Yeah.
We're going to start switching to the next person.
Okay. Yep. So we're just going to wrap this up. There's also one last thing. There's injection classifiers. You can run this on the sources, or you can run this on the query. If you run it on the query, it's going to identify if if there's an injection attempt in the query the user typed. If it's on the sources, it's going to see if there's an injection attempt in the sources that the AI is fetching from. So these are all the ways you can defend against this style of attack. I will get the slides up. I'll see if I can get the slides up so you can refer to them later. And thank you all for attending. I know I had more slides, but yeah, we're short on time. Yeah.
That's very clever.
Yeah.